Okay, perfect. Then thanks, Detlef, for your presentation. And you heard already all of the introductions, so I can skip all of this. As you see, here is pointer, preparing AllSky7 for photometric measurements, or let's call it part two of Detlef's talk. And as Detlef said, we made a lot of experiments already in our lab, but we also had, thank you. We also had a look on real night sky observations, which you will see here in the coming slide. So here there are two videos. I'll start them in a few seconds from AMS 31 and AMS 80. One is in the Bavarian forest, the other one is in Munich, so they are quite close together. You see roughly the same. Both camera 4, so they point into the same direction. And I'll start the videos. So you see time-lapse videos, the stars are moving, and then suddenly Vega will show up here. It's marked here in red, also here. Vega moving across the sky. So what I did here is I took 10-second means, I identified the stars, and then I summed up the digital values and subtracted the background. And let's have a look at the data, what we can see then. So this is Vega, so it's with a W, sorry for that, the German version. Vega seen for AMS 80, and you see basically the data for different nights. So this is simply J2000, and you see here in different colors the different nights. And well, what we see looks very similar for every night. So whatever we see, it must be at least the same thing for a few upcoming for a few nights. And to make it a bit easier to see what's going on, I plotted all of them into the same plot. So you see again here the nighttime, and with the different colors, you see the different cams. So there's cam 4, which you just saw before, and there is the camera 6 as well in black. So what we see during the night, our values are changing. Well, that's what we would expect, because there are certain conditions who change as well. So we have, for example, the air mass. So as you saw before, the star went down closer to the horizon. So there is an extinction effect, which is depending on the air mass. So this needs to be considered, of course. On the other hand, we have the vignetting, which Detlef just mentioned before. And here I said just want to see the radius to the center. And what we saw for the video before, we saw that Vega is coming in closer to the center and then moving outwards. So this is just the radius to the center. So if we have those plots, basically, we can have a look. What do we see here? Does it somehow make sense for us? Well, we see that there is this kind of peak. It goes closer to the center. We have here this peak. So yeah, I would say roughly makes sense. So let's have a look at another plot, because it's quite hard comparing those things if you just have the time here. So I plotted the radius to the center in pixel and again our data. And what we see here is starting with the red markers, the star is increasing in brightness and then it's going back down. But it, compared to the radius, it's a bit brighter later on. That's quite interesting, because just remember here, the star is moving closer to the the star is moving closer to the horizon, so we would expect extinction effect. So it should be the other way around. That was basically my first impression. So what is going on here? So we need to take a closer look. And therefore, I thought, okay, we have the vignetting effect. Let's have a look here. And I created flat fields. So 2 flat fields, one taken so in our lab with the integrating sphere, which Detlef just showed. And we have here the AVI and the MP4 version. You don't see a lot. So here with the a bit stretched colors. So now here you can clearly see structures. So this one is a bit smoother because of, well, here we have the compression. Let's move on. So here is the center marked. So you see, well, that roughly fits. You also see here, of course, on the edges, this also looks quite circular, but very interesting. What I thought is, okay, here in this area, it goes more into, well, like rectangular version with round edges. So there is clearly a non-radial structure going on. So does this help us explain what we can see? Well, we see again here the video with now here the overlay. of the flat field, you see again Vega coming in. Perfect, it moves out here. And then let's have a closer look. I marked everything a bit. Of course, for my plot, I did it versus the radius to the center. So we need to have a look at the same radii. So I chose here for the comparison this yellow radius to the center. And let's have a look at this position and the lower position down here of Vega. And then I marked this part with a cyan color. So this is like roughly the equal value. And for the first position, when it just enters, Vega, when it just enters the image or the video, it's more on the darker part, while down here, when we stop for the same radius, it's more on the inner edge, more on the lighter part. So therefore, yes, so when it enters, it's darker, and then later on, it's brighter. So, well, okay, we see that could make sense. I didn't do any, well, I didn't do the recomputation with the flat field so far. So let's see what the results are. But so far, so good. That's the question. Well, we have the AMS31 as well. And what we see here is, well, first of all, okay, similar pattern for every night. That's good. So it must be structural. Here, there were clouds. So, okay, we can also identify clouds. Perfect. However, so we see that we have the same somehow behavior for the nighttime with the air mass and the radius to the center, of course, because they have roughly the same location, looking in the same direction. But our data looks very different. And so far, I wasn't able to explain what was going on here. So therefore, more work for us to do. And also here, the comparison of the different version of the plot, we see it moves up in the beginning, similar to the AMS80, and then suddenly we have this peak going up. And here is something happening which we don't understand yet, but that's for the future for us to understand. And that's it. Thanks a lot, and I'm open for questions.
So that's what I call instant science, because I suppose the last slides were presented last night, maybe the night before, but certainly not longer. Questions for Michael? Jiří.
If you subtracted the background from your photometry, I mean, for example, in Munich, there must be more light closer to the horizon.
Yeah, I subtracted the background.
One more question in the back.
Okay, thanks. Sorry, maybe I missed the point, but is your photometry done after the flat field division?
No, so this was done before. So that was the reason I just had a look at the values, and then I thought like, okay, what is going on? How important are the different things?
Oh, okay.
So, and then I realized, okay, I see some behavior which points out to, okay, the flat field might be really important. Then I had a look at how the flat field looks and see like, yeah, we could explain this exactly with the flat field.
Yes, yes. So you can expect that your photometry will be improved by a very huge factor after you do the flat field division. That's for sure.
Exactly. Yeah.
Okay. Thank you.
Thank you. Yeah, thank you very much. How do you deal with the, let's say, differential gain of detailing algorithms inside the camera? Because you measured a star is a point source, and it is strongly influenced by the detailing of the camera. It is to enlarge the sharpness of the image. Do you switch that off, or do you measure it? Or?
So for those, I just used the standard settings and didn't change anything at all, because I really wanted to go for the settings and for the data we really have normally for everyday observation, because now doing completely different things, I mean, in structural, it's good so that we understand what's going on, but this was more like a test with the data which we really have, because if we do everything now for different settings, well, it's nice to have, but then we can't use the information for the everyday data.
Yes, but just a comment that it might be there might be errors due to the differences between the differential gain and the overall gain. Mm-hmm. So when you subtract a flat or multiply something, it's different than you have a spatial effect between neighbor pixels, and that's what the detailing is about. So that might be a source of errors.
Okay, yeah, perfect. I mean, perfect topic for a later discussion.
So one last question in the very back.
Did you measure linearity of that chip?
So we just did this basically, which I presented so far. So no other measurements.
Because it will be a very big impact to your measurement, the linearity of that chip, because most of the stars will be oversaturated, and then the photometry will be not realistic.
Yeah, so this is, I just picked Vega, but there are different stars having similar behaviors, so it's not the only one, also for fainter ones.
Okay.
But yeah, thanks.
Let's thank the speaker again.